Good afternoon and welcome to the 23rd Annual Exhibit of Hydrogen and Fuel Cell Technologies. We're in the technical forum here and we like to go into details because they're so important. There's so much complicated technology behind these units, behind electrolysis, behind hydrogen and fuel cells. Specifically, we're going to be talking about electrocatalysts as a key component for power-to-X technology. I like the X. I'm sure you'll explain it. We'll be talking to Dr. Immanuel Müller, who is manager of electrolysis at Fraunhofer-Institute for Manufacturing Technology and Advanced Materials. Welcome, Dr. Immanuel Müller.
Thanks for the kind introduction, and thank you. Yes, my name is Christian Müller, and I want to talk about electrocatalysts as a key component for power-to-X technology. And I'm from the Fraunhofer-Institute, IFAM in Dresden. To build up a hydrogen-based economy, it's mandatory to transform electrical energy into chemical energy. And therefore, we can use an electrochemical reactor that is shown here. This reactor is possible to transform this energy. Therefore, we feed this reactor with water, for example, or carbon dioxide, and also we have to apply a potential or current in order to drive the reaction forward. And then we'll get e-fuels or e-chemicals, meaning that we get methanol, methane, for example, hydrogen, or formic acid or ethylene. Such an electrochemical cell comprises of an electrode, an anode, and a cathode. These electrodes are divided by a diaphragm or separator in order to ensure that you get really pure products. And by the selection of our material we are using, we can define which product might be produced. For example, on the anode side, if we use nickel, we can produce oxygen. For example, if we want to produce ozone for wastewater treatment, then we can use bore-doped diamond, for example. Or we can use other catalysts, for example, to produce chlorine. Or we can use on the cathode side, where the reduction reaction takes place, we can use nickel to produce hydrogen, or we can use copper electrodes to produce methane or methanol if the reactor is fed with carbon dioxide, for example. Or we can produce formic acid. I want to give you two examples. The first is how we can produce hydrogen. We can do it with different technologies. In this case, I want to show you the alkaline electrolyzer technology. Here is given the overall reaction. If we apply a potential which is high enough, then we will get water and oxygen out of the electrolyzer system. The reversible cell voltage can be calculated to 1.23 volts. This is a scheme on the left side of such an electrochemical cell. If we look on the cost breakdown of such an electrolyzer system, then we see that the main part comes from the electrodes, the anode as well as the cathode. So if we want to improve or make the whole technology cheaper, we have to reduce the cost, and the main factor are the cathodes and the cathode and the anode. If we look on the electrochemistry and on the operation conditions, then we have two important parameters. This is the cell voltage and the current density. The cell voltage defines our energy which is needed to produce hydrogen, so it's directly related to the costs. And the current density defines how much hydrogen is produced per second. You see here an image of such a facility where I think more than 10 electrolyzers are used to produce hydrogen. There are different manufacturers also here at the fair. So there are some demands for such an electrode. The degradation rates have to be very low, the lifetime stack should be very high, and also the electrochemical activity should be in the range between 1.8 and 2.2 volts at a current density up to 0.6 amp per square centric meter. So there are two approaches to produce or develop very good electrodes. The first one is to increase your intrinsic activity. The second one is to enlarge your surface area. The second one is much easier and much more gives you better results. So what we can do, we can enlarge the surface up to a factor of 10,000. What this means is if you increase your surface area, then you have more reaction sites per surface area where a reaction can take place. And so you can produce more hydrogen per on the same surface area. That's the idea behind this. So we are able to produce different structures in the range of 100 nanometers to 100 micrometers, and we get roughened surfaces. And these roughened surfaces have a much larger surface area. And we can structure different surfaces, for example, flat surfaces, or we can structure these expanded meshes. We can use foams, you see here, which can be also produced at our facility, and we can also modify these foams. Also, it's very important if you want to develop electrodes that you have the right technique to produce it. So it should be a scalable production technique. We use powder metallurgy as one example, where we start from a powdery precursor and which is sintered on a flat surface or also of a porous surface. We can use electroplating, where you deposit or electrodeposit and dissolve the species onto your surface area by varying your parameters, your composition of the electrolyte. You can produce flat surfaces, also structured surfaces. We also use laser ablation process, where you use a femtosecond pulse and can produce in one step directly a very roughened surface area. See this in this image here. Also, we use rapid quenching techniques, where you can produce continuously amorphous ribbons, for example. Just give you one example. We have developed different materials in different projects, and this is just an example of this. Shown is here on the diagram on the left side, the potential of the electrodes versus the time. The dashed lines give you the reversible potential for the oxygen evolution in the case of the blue dashed line, and the red dashed line represents the reversible potential for the hydrogen evolution reaction. We have developed electrodes with very highly efficient and also have a very long-term stability. For the oxygen evolution reaction, we have used these femtostructured materials based on a nickel-cobalt alloy. You see these cone structures here, which have a very high surface area and are very active. Also, we have developed these roughened nickel materials, which also have a very high efficiency. If you calculate the cell voltage of such an if you use these electrodes in an electrolyzer and you calculate the cell voltage, you see that you get a cell voltage of 1.6 volt at a current density of 3000 amp per square meter. This means that you need around 45 kilowatt hours per produced kilogram of hydrogen. And assuming electricity cost of around 0.1 euros per kilogram per 0.1 euros per kilowatt hour, you can get hydrogen. You can produce hydrogen for less than 5 euros per kilogram. The next example and the last example I want to give you is that you can also use electrocatalysts to use carbon dioxide as a feedstock and renewable energies to produce e-chemicals or e-fuels in one step. So you have the cell and you feed the cell with carbon dioxide and also with your potential with electrical energy, and then you can produce in one step chemicals, for example formic acid, ethylene, or you can produce methane, methanol, or ethanol. We have an electrochemical cell at our facility where we can test materials. In this case, we have used a setup which resembles a zero-gap electrolyzer system. This is a scalable technology, so you can produce many stacks or many cells to one stack very easily. And you have here on the downs, you have the inlet for the saturated carbon dioxide electrolyte, and here you have the two outlets for the liquid product as well as for the gaseous product you get out of the reactor system. Just to give you one example, we have produced copper foams at our facility. You see these images here. They have a pore size of around 2000 micrometers, and we have electroplated these foams with tin, which is a very good catalyst to produce formic acid. And I will show you the result on my last slide, I think. You see here is plotted in the left figure is plotted the current density versus the cell potential. And if we increase the cell potential, we see that after a certain point, the current density increases, which tells us that the reaction takes place. And you see that the reaction increases by increasing the cell voltage, and after around, I think, 3.3 volts, we have a limiting character, so there's no further increase of the current density by increasing the cell voltage. And if we analyze the product we get during this reaction, we see that at the cell potential of 3.25 volts, we have a current density of 130 milliamps per square centimeter meter. And the Faradaic efficiency for producing formic acid is around 30%. So the partial current density which produces formic acid is around 40 milliamps. Some authors state that you need around 50 milliamp per square centimeter meter for industrial production of formic acid with this technology. So we are very close to this threshold for industrial production. You see also that if we plot the Faradaic efficiency versus the cell potential, there is around 2.5 volts, the maximum of efficiency, and after this point it decreases. So to sum up my talk, I have shown you that electrocatalysts are essential for the energy turnaround because we can transform electrical energy to chemical energy, for example hydrogen, or to methane, to methanol, or to valuable chemicals, for example formic acid or ethylene. At our institute we are able to test and as well to develop electrode materials on different scales. You see here these different setups we have to test electrodes at our facility, but we are also able to produce these materials at our facility with different production techniques I have shown you. And we were able to develop long-term stable electrodes, and the cell voltage was around 1.68 volts, and this means that we need around 45 kilowatt hours to produce 1 kilogram of hydrogen. Also, I've shown you that we can convert or transform carbon dioxide to a valuable chemical, in this case formic acid, with a simple reactor by using just only copper foam, which is electroplated with tin. So this was my last slide. I would like to thank you and Damaris for your kind attention, and thank you.
Do we have any questions from the audience? So,
do you have already an industrial application of producing formic acid in the electrolysis?
No, it's not industrial scale, it's just, let's say, around technical readiness level, perhaps 3 to 4. Depends on if you look only on the cell, on the whole system to get formic acid out of it. That's how you see it.
Yeah, thank you for your interesting talk. These really highly structured catalysts, which are very efficient, you say, but how long do they last? What do you do? What are your strategies to increase their stability over time?
Yes, normally you have problems with brittle catalysts, for example, due to the hydrogen evolution reaction, you are right. So we have used this laser ablation process where you have still a solid material. So we have these cones, but these are very mechanical stable, even if you produce hydrogen, though these eruptive release of hydrogen bubbles from the electrode did not really affect your catalyst. It's very stable in this case. If we use other catalysts, sometimes nickel electrodes, you have this problem that they're not so stable. But also there are ideas to stabilize this material. We have developed in projects, or we are developing, yes. But very good question.
are there any other questions? Yes.
Thank you for your presentation. What is your operating temperature for the reactor?
For which reactor? For the carbon dioxide reduction, or in this case it's around
carbon dioxide.
The hydrogen or the carbon dioxide?
Yes.
The carbon dioxide. The temperature is around room temperature, 23 degrees. Because if it's too high, the temperature, then the concentration of carbon dioxide in the solution goes down. So you have to balance your temperature. Yes.
Any other questions from the audience? I always find material science so interesting and yet again frustrating because in order to talk technology in the fine region, we miss the possible applications sometimes. I was listening to you and I was thinking, oh, increasing surface area, that actually allows you to create a unit with a smaller footprint.
You are right.
And as soon as we go to the market potential, this is one of these great debates. How are we going to create a hydrogen highway? Shouldn't we be doing local electrolysis? And here, using existing gas stations as a location means you need a device with a small footprint. So little things like this fascinate me. That's one thing. Another thing is the costs that you mentioned. If we're talking about hydrogen production, €5 per kilogram. That's not exactly the lowest price right now. Depending on how you're doing it, of course, and whether you're working towards a small footprint, the price is not the only thing we have to consider. So if it's not the lowest price, are there other advantages for your production of hydrogen?
The long-term durability, absolutely. If you have maintenance costs, for example, you can reduce the whole cost of ownership and the operating costs you have for electrolyzer systems. So I think long-term stability of electrodes and long-term efficiency is a major point you have to address, and we are addressing at the moment. So this is absolutely advantage of these catalyst materials.
And another thing, as we approach commercialization, of course, the cost per unit has always been prohibitively expensive. It's not all our fault, of course, because if we could mass produce right now, we'd have a large market. Production costs sink drastically in the industry. Now, this is not your fault either. But one of the interesting things is the catalysts themselves are a huge expense factor. Have you been able to reduce costs by using different materials in a significant way?
Let's say this is a difficult question because to calculate this, you have to make some assumptions and then you get the number and you don't really know if you can trust this number. So we have made some calculations, but due to confidentiality reasons, I cannot talk about at the moment about the cost of such an electrocatalyst.
This is interesting because, of course, the last question would be, if we go back about 10 years, we had various manufacturers here and they were all trying to corner the market with their specific technologies. If you ask them, so what's your catalyst? They would not answer the question. Now there's a large form of cooperation. People share knowledge. Also, of course, the material scientists, they have to work for various suppliers. So even if we don't know publicly who does your catalysts, privately everyone knows. Is there a lot of cooperation now and sharing in the market in terms of the knowledge base which applies to electrocatalysts?
I don't think so. Normally you are forced to make some publications if you are in public projects, and then you get some information, but I think nobody of these industrial electrolyzer producer will tell you which electrocatalyst he is using. So if you are in a project with these, then you get some information, but it's very difficult. But I understand this topic because it's your... Yes, it's... You cannot give anybody what you are doing. It's very difficult to do this. So.
Yeah. And especially if you're partnering with the industry and relying on co-financing of research and development, there has to be some agreement that the spin-off effects of your research can be applicable within certain industries with certain advantages for certain manufacturers.
Yes, yes.
Okay, so now we get the real side of this, of course. Science, though, is at the forefront of this interesting industry. We have been talking to Dr. Immanuel Müller, manager of electrolysis at Fraunhofer-Institute for Manufacturing Technology and Advanced Materials. It's been a pleasure. I hope we see you back here next year with more candid information.
Yes, thank you.
Thank you. And we'll be continuing in a few minutes, so stay tuned. Up next on the stage, we'll be talking to Michael Müller, who's Director of Engineering Sciences at Mott Corporation, about design for manufacturing and using porous metals. Stay tuned, have a drink.